welcome to your deep dive, I guess we could call it, into this fascinating world of quantum computing.
Mm-hmm.
We're going to try and get to the heart of these incredible machines,
Yeah.
And specifically, we're talking about these qubits.
Right.
Our guide for this journey is a paper by a former physicist, Kawamura Akihiro.
Okay.
And he's catching up on this field after a few decades away. So this is kind of perfect for somebody like our listener,
Yeah. I think that's a great...
who may be in a similar boat.
Yeah, Kihiro's background is really interesting, too, because he actually used to use electron spin resonance to study semiconductors.
Wow.
And he even talks about going into a reactor with a Geiger counter and liquid helium.
Wow, that's dedication.
Yeah.
So to start us off,
Right.
what is a qubit?
Well, you can think of it as the quantum version of a bit.
Okay.
The basic unit of information in classical computing.
Right.
But instead of being limited to just a 0 or a 1, a qubit can exist in what's called a superposition of both states simultaneously.
Mm-hmm.
And this is really one of the key things that makes quantum computing so powerful.
That sounds a bit like Schrodinger's cat, this thought experiment,
Yeah.
where the cat is in this blurry state of both alive and dead until we look in the box.
Right.
How does that actually work with a qubit?
It is a mind-bending concept,
Yeah.
but it is at the heart of quantum mechanics.
Mm-hmm.
So let's say we have a qubit representing the answer to just a simple yes or no question. Until we measure it, that qubit holds both the yes and the no possibility
Simultaneous.
at the same time.
Wow.
And this is what allows quantum computers to explore many potential solutions at the same time, giving them just a massive advantage for certain types of problems.
So one qubit can explore two possibilities at once.
Right.
What if you have multiple qubits?
Then the possibilities just multiply exponentially.
Okay.
So with 2 qubits, you can explore 4 possibilities.
Mm-hmm.
With 3 qubits, you have 8, and so on. And this is where the real computational power of quantum computers becomes apparent.
That's pretty incredible. So I understand that there are different ways to actually physically create these qubits.
Absolutely. Akihiro focuses on 3 main systems:
Right.
electron spin,
Mm-hmm.
photon polarization,
Okay.
and superconducting circuits.
Okay, let's start with the first one.
Yeah.
Electron spin.
Okay.
Which ties back to Akihiro's own research.
Right.
So what is that?
So imagine electrons like tiny spinning tops,
Okay.
each with their own little magnetic field.
Mm-hmm.
And we can use this spin, which can be up or down, to represent 0 and 1.
Okay.
And by applying microwaves, we can actually manipulate that spin, essentially flipping it between those states.
Wow.
This is the basis of electron spin resonance, which is the technique that Akihiro was using in his research.
So you're basically controlling these tiny spinning magnets
Yeah,
to store and process information.
precisely.
That's wild.
Yeah.
Okay,
Yeah.
and that's just one of the 3 ways. So what about the other 2?
Another approach is to utilize the polarization of photons, which are particles of light.
Okay.
Light can be polarized in different directions, which, again, we can use to represent 0 and 1.
So you're kind of manipulating the direction of light waves
Exactly.
to encode information.
To encode information.
Okay, that's method number 2.
That's method number 2.
Method number 3.
Now, the third and most common method today involves what are called superconducting circuits.
Okay.
And this is where things get a little more complex.
All right, I'm ready to lay it on me.
Okay.
How do superconducting circuits work as qubits?
So these circuits leverage the unique properties of superconductivity,
Okay.
which is a state where electricity flows with 0 resistance.
Uh-huh.
This allows us to create very specific energy levels within the circuit.
Mm-hmm.
And these energy levels can be used to represent 0 and 1.
Right.
And we can manipulate them to perform quantum calculations.
So we've got spinning electrons.
Yep.
We've got polarized light.
Uh-huh.
And we've got superconducting circuits,
Right.
all being used to create these qubits.
It's pretty amazing.
There's a lot of variety in the way these qubits are made.
Yeah, there is.
Is-
Physically, there is. And
Right.
each system has its own advantages and challenges. But what unites all of them is their ability to exist in this superposition of states, which, as we talked about, is what gives quantum computers their incredible potential.
This is all very exciting.
Yeah.
But if a qubit can be both 0 and 1 at the same time,
Right?
how do we actually get like a definitive answer
That's a great question.
out of a quantum computer?
Yeah, and it brings us to one of the most fascinating and perplexing aspects of quantum mechanics,
Okay.
the so-called measurement problem.
All right, well, let's dive into that in
Yeah.
the next part of our deep dive.
Okay, so this measurement problem.
Right.
This is a fundamental concept in quantum mechanics that can be a bit tricky to wrap our heads around. But essentially, while a qubit is in that superposition, it's like it's holding all these multiple possibilities at once.
Okay.
But when we measure it, that is when we actually try to observe its state.
Right.
It collapses into a definite 0 or a 1.
So the act of measuring forces the qubit to choose.
Exactly.
Yeah.
It's as though the act of observation forces that quantum system to settle into a single reality.
I see.
And what's really interesting is that this collapse is probabilistic.
Okay.
Meaning that we can't actually know for certain which state it'll choose.
So that sounds like a bit of a wild card when you're trying to build a reliable computer.
Yeah.
I mean, how can you be sure of your calculations if the result is essentially based on chance?
Yeah, it's a significant challenge in quantum computing, and one that researchers are actively working to address. So clever algorithms and error correction techniques are being developed to try to manage this inherent randomness. You know, you can almost think of it like trying to build a house of cards on a rocking boat.
Right.
You need strategies to maintain stability.
I like that analogy. Okay.
Yeah.
Now, before we move on,
Sure.
you mentioned this other mind-boggling concept called entanglement.
Yes.
What is that all about?
Well, entanglement is perhaps one of the most bizarre and fascinating aspects of quantum mechanics.
Okay.
So imagine two qubits that are entangled. This means that their fates are basically intertwined no matter how far apart they are physically.
Intertwine, how?
If you measure the state of one of those entangled qubits, you instantly know the state of the other one, even if they're miles apart.
Really?
It's as if they have this invisible connection.
Wow.
Sharing some kind of secret code.
That sounds almost like telepathy.
Right.
How can two particles be connected like that across any distance?
It's one of the great mysteries of quantum mechanics.
It really is.
Einstein himself famously called it spooky action at a distance.
So spooky or not, how does entanglement actually play a role in making quantum computers powerful?
Well, entanglement is crucial for many quantum algorithms.
Okay.
So by entangling multiple qubits, you're creating this network where their states are all interconnected.
Right.
And this interconnectedness allows quantum computers to explore many possibilities simultaneously,
I see.
leading to significant speedups.
So it's like having a team of synchronized swimmers
Exactly.
moving in perfect harmony rather than individual swimmers.
Yeah, that's a great analogy.
Okay.
And this coordination is what allows quantum computers to tackle problems that are just simply out of reach for classical computers.
Now, going back to our source, Akihiro seems particularly interested in something called the Riken quantum computer.
Right.
Can you tell us about that?
Yes. The Riken Institute in Japan is at the forefront of quantum computing research.
Okay.
They are developing a superconducting quantum computer.
Which, as we've discussed, is one of the leading approaches for building these machines.
Yeah, it seems like superconducting circuits are the popular kids on the block.
They're certainly getting a lot of attention.
Yeah.
Superconducting circuits offer advantages in terms of controllability, scalability, and integration with current technologies. But it is still very early days.
Right.
And other approaches like trapped ions and photonic quantum computers are also being actively developed.
So it's not a one-horse race yet.
Exactly. Different approaches have their own strengths and weaknesses. For instance, photonic quantum computers could be ideal for communication and networking because of their connection to light, while superconducting circuits might excel at complex simulations.
So the choice of qubit type could depend on the specific application.
Exactly.
Interesting.
And as the field continues to develop, we might even see hybrid systems that combine the best of different technologies.
That makes sense.
Now, our physicist, Akihiro, he has a background in studying electron spin for semiconductors, which he refers to as quantum solid-state physics. Is that a recognized field?
Absolutely.
Okay.
Quantum solid-state physics explores the quantum behavior of electrons in materials. It's a foundational field for much of our modern technology. From transistors and lasers to, you guessed it,
Yeah.
Quantum computers.
So Akihiro's past research is actually very relevant.
Is.
To the future of computing.
It is. And his journey of rediscovering this field after being away for a while really reflects, I think, the dynamic nature of scientific exploration.
It's reassuring to know that even experts are always learning.
Always learning.
This has been a fascinating dive into the world of qubits.
Yeah.
What would you say is the most important thing for our listener to take away from all this? Well, I think the biggest takeaway for me is that quantum computing, it's not just about building faster computers.
Right.
It's a completely new paradigm.
Yeah.
Like a fundamentally different way of approaching information and computation.
That's an excellent insight. I mean, it really does challenge our conventional understanding of, how computers work. And as we've seen, it draws from some of the most just mind-boggling concepts in quantum mechanics, like superposition and entanglement.
Yeah. It's both exciting and a little intimidating, to be honest.
I understand.
It's like we're standing at the edge of this vast unknown territory.
I agree. But think of it this way. We're not just passive observers here. We're active participants in this unfolding story of quantum computing.
You're right. And even our physicist, Akihiro, he's on his own journey of rediscovering this field after years away.
Right.
It reminds us that learning is a continuous process.
It is.
Especially in such a rapidly evolving area.
Absolutely. And it really highlights, I think, the importance of staying curious, being open to new ideas and challenges. I mean, that's the spirit that drives scientific progress.
Absolutely. Speaking of challenges, it seems like building a stable and reliable quantum computer is incredibly difficult.
It is.
I mean, we've talked about this measurement problem.
Right.
The probabilistic nature of these qubits. And all the technical complexities of actually manipulating these quantum states.
Yeah, it's a monumental task, for sure. It's like you're trying to orchestrate a symphony of subatomic particles, each with their own unique set of behaviors and quirks.
I see.
But the potential rewards are immense.
So for someone like me, who isn't a physicist, but is fascinated by the possibilities, what does this all mean?
Well, it means that you're living in a truly remarkable time. Quantum computing has the potential to revolutionize just countless fields, from medicine and material science to artificial intelligence and beyond. I mean, imagine personalized medicine that's tailored to your specific genetic makeup, or new materials with properties that we can barely even conceive of today.
Those are some pretty incredible possibilities.
They are, and let's not forget the potential impact on cryptography and cybersecurity as well. Quantum computers could break the encryption codes that we currently rely on for secure communication.
Wow.
But they could also lead to the development of new unbreakable codes.
So it's a double-edged sword.
It is. It's like we're on the verge of a technological revolution.
It really does feel that way.
It does, and while it's still early days, the pace of progress is really accelerating.
Right.
I mean, new breakthroughs are happening all the time.
Yeah.
Pushing the boundaries of what we thought was possible.
This has been an incredibly insightful deep dive.
It has.
As we wrap up,
Yeah.
is there anything else that you want our listener to kind of ponder as they continue their own exploration of quantum computing?
I would say I would encourage them to stay curious and to never stop asking questions. Quantum mechanics is a field that's full of mysteries and paradoxes.
Right.
And it's precisely those unanswered questions that are going to drive the next wave of breakthroughs and discoveries.
That's a fantastic thought to leave our listener with. And remember, Akihiro's article mentioned that Japan's Aiken Institute is developing a superconducting quantum computer.
That's right.
So, it might be interesting to explore the advantages and disadvantages of all these various physical systems that are being used to build these machines.
Yeah.
I mean, what other real-world applications might this technology unlock in the future?
Right.
Keep those questions in mind as you continue your own quantum journey. This deep dive may be over, but your exploration has just begun.